Right. This is what we do. Raphtory is a temporal graph system. It does many things, but here we go. Um, I am one of the lead developers with Raphtory. I've been a Java dev all my career. Switched to Rust a year and a half ago. Um, Now, I'm going to give you some examples in the case of tracking illegal money laundering. Not that there's any legal kind. There we go. Um, so let's dive right into it. So, higher level view, we're an in-memory. We have a paid version that could write to disk. Node IDs can be strings or numbers. We keep track of them. You don't have to worry about that. We have composable temporal views at any level, graphs, edges, nodes, or properties. We can index your properties. We have layer support, we have GraphQL support, and all the APIs are available in Rust, Python, and GraphQL. So we're trying to make it super easy for you to deal with anything related to graphs and anything related to temporal graphs. Right, we can load here's an example. You can load some data from a Parquet file. You just give it the source, destination, time columns, give it some the properties for the edges, and say a column that you want to pick, say which one of them is the layer. You can quickly get some basic stats, but you have the graph, count the nodes, edges, and temporal stuff, and see which one's the earliest, which is the latest time across your edges and your edges in the graph. In this case, this is this is the one of the cases where we use Raphtory to track money laundering perpetrated from Azerbaijan. Um, and we use their data. And here's some example about that. Like this is you've loaded your data and you go, okay, give me the node. And all you have to do is just say which one you want. We'll handle that for you. Um, you can find out things about your nodes, like give me my node's name, earliest time, give me the degree, like whatever, how many edges do I have? Fun fact, our edges refer to what we think about as the static graph, whereas the events in the temporal view are attached to those edges, and to those nodes. For example, you can say this node, give me all its internal edges, and then give me the name of the source that's been paying me money, and then go over all of the history of transactions that I have over this relationship, and then extract this property and then sum it up to see over a period how much money have I received. But I can do much fancier things. I can say, give me an edge, and then do a rolling window over the edge, and then look specifically at every rolling window and do the same thing. For example, in this particular scenario, you can track how the activities increase between these two counterparties across time, and all you have to do is just say, given the rolling window, given the sum, given the properties, all these views are handled for you. We have the the normal kinds of algorithms that one would have with graphs, all these shortest path, bit rank, cycles. Some of these things I don't understand because they're written by cleverer people than I am. I am mostly in the core data structures of things, in the core storage layers of things. Um, so we have scientists who work that are implementing algorithms for us. For example, temporal motifs is one of the more fancier ones we've got. Um, this is one of the examples. This is a paper that uses Raphtory to track temporal motifs across data sets like the Alpha Bay dark network. And it's also been used in the previous money laundering case that I sent. And I'm not very familiar with it, but I have been told that it allows us to track cycles, and it allows us to track easier suspicious activities across various networks. And of course, all of this can be all of this provides more information if you track how these interactions happen across time. The link to the paper, I will post it in the chat as soon as I can. Moving on. So as I said, you can make many graph views. You can say, give me all the nodes from from this point to this point over these layers. Or give me this graph, give me a sub view of the graph, with these node types, and then run weakly connected components just on that. You can have nested filters. You say, give me the rolling window for this graph, so it generates an iterator of graphs that hold the data for a month. And then inside that, you can generate edges and have a rolling iterator for every 2 days. You can basically track the interactions across a graph, just like that, and do whatever computation you feel like it. We also have indexing and searching. We use TanTV for that. Um, you can you can index any sub view of the graph or the entire graph. You can search not just edges. You can search edges and nodes. I think you can pass in predicates that are relating to properties, and then explore your edges. We also do GraphQL. All the APIs from Python and Rust are available in GraphQL. You can push your graph to your servers. You can start up a server and just push graphs to it, and then have other people read these graphs and work with them. We currently use this in one of our clients' deployment, where we have an analytics pipeline that will push graphs and serve them to a team of data scientists. Think about it as a repository of graphs. It's easy. Like, you just start a server and that's it. And then you can query it if you have a graph on it. You can just graph node, give the properties, graph, give me an edge, or you can just hop around. Just go from all the nodes of this type, give me their neighbors. This is all available in the library. Now, a quick word about how do we get here. Initially we had a distributed system that started with this paper. There was a different paper that started all. This is a reinterpretation, a rewrite of that paper to reflect the changes and the decisions we've made with Rust on this link. Initial versions were Scala, were distributed. We had cool things like event source, cloud native, vertex-centric algorithms, but we were kind of slow. And one of the big problems was that since we are kind of targeting the Python crowd, which, as you've clearly pointed out, is the lion's share of scientific things in software, we had to do crazy things to interact with pip from the JVM. We used Py4j, JPipe. We install an entire JDK onto people's side packages and downloaded all the jars. Whenever you did an import, basically did a bunch of stuff that I found just terrible. But the interop is slow between Java and Python. It's quite horrendous. We tried functional programming for a while. That definitely did not scale to the performance requirements that we had. We tried to use Arrow and use some Java for our storage, and it created an immense amount of problems, namely because the Java Arrow API is kind of terrible, and it doesn't offer us any sort of the security, the safety of Java. It just basically goes ahead and messes with pointers. It can break in very weird ways. It uses too much RAM. We needed large EC2 boxes for very small graphs. January 23, we switched to Rust. We use Pyo3, which is fantastic if you want to write Python from Rust. We can load large graphs on a laptop. The transition from Scala was quite easy. Scala shares a lot of the things that Rust has, from results, from options, from pattern matching, from a strong type system. Cargo, It's just great. It took us about 3 months to fully rewrite, and it's been solid. We have a paid version deployed with a customer that supports terabyte-sized graphs. We're testing it to 17 billion. We tested 17 billion edges, but we could do more than that. We're using Arrow for that version. We are deployed since recently with one of the world's largest banks. Um, I think that's it.
Wonderful, thank you very much. Some impressive stuff you've been working on there. Um, Again, I'm starting to see some thanks coming in chat. If anyone's got any questions, feel free to type them in the question and answer box. Which I'm seeing nothing has come into yet. Um, so I can ask a question I have. Is there any limit to like the maximum size of kind of graphs that you can handle with your software?
As I said, we tested them up into lower terabyte sizes. I think through about 3 terabytes that we've tested. In essence, no. If you have the space, we will gobble up your graph and make it very pretty. And one of the advantages, but this is the one that goes to extremely large graphs is the paid version. The open source version does fairly large graphs in hundreds of millions of edges. So, but the focus here is not just that we can do large graphs, and I know our scientists work with large graphs on their laptops. It's just that I don't know of any other library, both either Rust or Python, that allows you to work with graphs so easily, and have the high level APIs to sort of slice and dice your APIs in such a way that you can sort of either have the whole graph, and there is no cost to these projections. They're instant, right? They're all lazy projections. Um,
Yeah, thank you. Okay, we had a question come in, which I'm going to ask because there is no next talk that you can type answers during, so I'm going to ask you the question that's come in. It says, can you quickly describe a temporal graph? Is it like a forest of graphs indexed by time, or are there temporal edges between nodes?
so I can describe it. I think the second part is that there are the temporal graph has two main sides. So it has a static graph, as you know it, all the interactions that have ever happened. And every edge and every node and every property knows when does it exist. So if you imagine from 0 to 1 million, if you wanted to view a graph between, I don't know, 500,000 and 800,000, then we will give you a view of that graph that only the edges, the nodes, and the properties that have timestamps within those time intervals. Um, there we have some much fancier graphs that I didn't mention that are graphs that support deletions in the sense that a node or an edge can pop in and out of existence, and you can see that in some scenarios. For example, we use this for HMRC again for money laundering, where you have directors that come in and out of companies. So we modeled edges. It's a problem that you often don't think about it until you have to track money across wide networks, and you say, well, this guy's been director, and then he stopped being a director, and then he started being a director again. So the ability to view graphs, because you can take slices of graphs, or you can do them rolling, and you want to see where the influential peoples across. We have quite a few algorithms to determine um, influence across graphs. Uh, yeah, there's a lot to say within 10 minutes. It's kind of rushed, and I'm throwing a lot of information at you. But yeah, give it a try. If you have problems with graphs, we're more than happy to help.